Perhaps let's get started now. It's my pleasure to introduce today my academic brother, Ilias Zadik. Ilias is an assistant professor of statistics and data science at Yale University. His research mainly focuses on the mathematical theory of statistics and its many connections with other fields such as computer science, probability theory, and statistical physics. And before Yale, he held postdoctoral positions at MIT and NYU, and he actually received his PhD from MIT in 2019. So great to have you here, Ilias, and the floor is yours.
Thank you very much, Martin. Thank you very much for the invitation. Okay, so let's start. Okay, so right, so the topic of this talk will be the fundamental limits of recovering planted subgraphs. So it will be about the fundamental limits of recoverability of random structures. I will obviously explain everything. I don't assume you know what the planted subgraph model is about. And let me say before I start that this is joint work with three amazing PhD students at MIT, actually, Daniel Lee, Francisco Pernice, and Amit Razaman. Okay, and yeah, please ask me if you have any questions or whatsoever throughout the talk. Okay, so the general setting is parametric estimation. So this is where the whole talk will take place. So let me take a moment to perhaps explain it to you or remind you what this is about. So parametric estimation is as follows. There exists some hidden parameter theta star that is sampled from some prior P. So this is called the prior, like where the hidden parameter is sampled from. And this is supported on some parameter space, theta. So let's assume it's a Euclidean parameter space, like inside an R to the n. And then we make some observations, D, that are basically coming from another probability distribution indexed by this theta star. So like, from this theta star, you get some data. So this is like the data. And the goal is basically parametric estimation. Can you go from the data to theta star? Like this is the question, the inverse problem. And this is a very canonical problem, and there are many perspectives on it. And the perspective we will follow will be the minimum mean square error perspective, which is basically judge how well you can do in recovering this parameter theta star in the mean squared error sense. Like you want to go find some estimator, the best possible estimator that use the data set and comes as close as possible to the true parameter in the L2 square sense, and you take expectation over everything. So this is called the MMSE, the minimum mean square error. So the minimum over all A measurable estimators in this problem. And the good thing is that about this model is that we know actually the optimal estimator. So the optimal estimator is actually given by essentially like this estimator here, which is colloquially called the posterior mean. And if you want to think, to understand what's the posterior mean, I mean, the definition is as follows. You basically take the average or the mean over the distribution, which is called the posterior, which is just the probability distribution of theta star given D, right? So this is like the distribution you have, you want to guess theta star given D. So you're basically, just take the conditional distribution given D on theta star and you just average it out. That's called the posterior. Okay, so what is the catch here? The catch is, of course, that in fact is hard to calculate this object, let alone in specific models. So therefore, it's actually hard to compute the MMSE in many models. It's hard to compute it, and even analytically. And the specific aspect we will care about here is, in fact, the high dimensional limit of this object, which is even harder in some ways. So specifically, we will care about problems that live in a high-dimensional space, like for large enough n, and this is therefore index of n. So that adds another layer of difficulty. But that being said, as I kind of already hinted, this is a very fundamental object, the MMSE of a parametric estimation problem across statistics and information theory, in probability theory as well. It's a very canonical object that really measures this thing, how well you can recover the parameter. And that being said, we've seen big successes over the last decades on understanding the MMSE. In fact, we've seen exact computation of the limiting MMSE, like as n goes to infinity, for many canonical high-dimensional models. And some such successes, perhaps some of the biggest ones, happen, for example, in the compressed sensing problem. So these are stylized models that yet still is hard to get the answer. So, for example, compressed sensing, like in where there's like basically a signal hidden in Gaussian noise and Gaussian features. Like we initially it was conjectured by physicists and later proved by mathematicians, the exact formula for the MMSE. And similar for the so-called spiked matrix models, which are versions of principal component analysis. Now, that being said, we've seen successes, and the successes more or less follow the following paradigm. More or less, they're based on statistical physics techniques. Usually, there's a certain conjecture using the heuristics like the replica symmetric trick or the cavity method, if you're familiar. And later on, there are proofs using, again, statistical physics techniques, but from the rigorous mathematical spin class theory, for example, or statistical physics literature. For example, Guerra interpolation is a canonical technique in these proofs. What we're going to see in this talk, we're going to see a different perspective on calculating the MMSE for a quite canonical parametric estimation task, high-dimensional parametric estimation task, which is called the blended subgraph model, which we are able to get, if you want, without statistical physics perspective. So it's at a different perspective of how to get the fundamental limits of estimation. And this is happening partially because we try to do this without using statistical physics techniques, but if you want, like purely probability and combinatorics. But also it's happening also somewhat inherently because like this is a heavy combinatorial and sublinear prior, and therefore inherently most statistical physics techniques do not apply in this model for various technical reasons that I'm happy to talk offline or if you ask me about.
Ilias?
Of course.
Sorry, does it make sense to think about a frequentist version as well, where you don't have this kind of prior?
Right. Definitely. First of all, in the generality I'm presenting, definitely parametric estimation does make sense in the frequentist point of view. For the results I'm going to describe, we do use the prior. So I would say that, like, for results I'm going to describe, not directly, but definitely, I mean, the variants are not probably very hard to build. But I haven't tell you what results I'm going to prove. But for example, for the statistical physics approaches, the prior is extremely important. If that's what you think. Yeah.
Thank you.
Okay. Right. So now, moving forward, I need to describe to you what's the blended subgraph model, right? I don't assume you know it, and of course I need to go through it. But instead of doing this like right away, I will do this in a slower manner by first describing you where this all started, this blended subgraph model started, which is basically a model hopefully you've heard or you might heard of, which is the blended clique model. So what is the blended clique model? It's a toy version of community detection. Introduced by Jerrum in the 90s. And the model is behaving as follows. There exists basically your observation space is an undirected graph of n vertices. And what happens is that, let's construct the observation G. The observation is constructed by first choosing k out of the n vertices uniformly at random. Okay, so this is k out of the n vertices. And then you basically include all possible edges between the k vertices. In other words, you form a clique or a fully connected subgraph. And then what happens after you form this fully connected subgraph, you are introducing every other possible edge in an independent fashion by tossing a coin with probability p. So anything that has one node in and one node out, you include it with probability p. Anything that was two nodes out, you include it with probability p independently. Mathematically, this is basically take the union of an instance of a so-called GNP. So that's the Erdős distribution n comma p. That's the mathematical version of what I just said. Independent toin causes for each edge with probability p. Okay, I hope the model makes sense. And the task here is, from G, can you recover this hidden blended clique, right? That's the blended clique. can you recover, like just by observing at Z, where the planted clique is located? Perhaps it's good to say some quick things. So if P is 0, right, there's basically no other edge with probability 1. This is extremely easy, right? You just see anything that has connected with an edge is part of the planted clique. So you can recover the vertex and the edges of the planted clique very easily. If P is 1, on the other hand, right, there is no hope on this, right? You just see all the edges of the n vertex undirected graph. So you have no hope to see any community structure. So this is impossible. And really, like, you should think of it as P as the noise level, right? As the P increases, like as goes like from 0 to 1, so maybe that's a bad figure, oops. As P increases, okay, maybe let me just put it here. As P increases, the problem becomes more difficult, right? So there's more and more noise. Okay. So, right, so that being said, let's continue. And let's instantiate it in some specific value of k, because just to tell you what we know about the MMSE. So I'm choosing it basically logarithmic. I'm choosing the numbers appropriately to have nice numbers in what will come. So 2 log with base to n, let's say. So very tiny clique. Then basically you can ask what's the MMSE. Okay, so let's go back to the MMSE. The MMSE, you try to recover, okay, you need to put it in vector notation, okay, and you do this and you rescale things to put it, let's say in 0, 1, the MMSE. So this is like in the indicator, this is just the indicator of the clique edges. Okay, etc., and you rescale it. But all these are details. So instead, I want you for the whole talk to understand the MMSE in the following way. If you rescale it appropriately, this is really equal always to 1 minus, it's approximately equal, but you should keep it like this in your mind, 1 minus the expected value of the best fraction of edges of the planted clique that can be recovered from G. So that's how you should think about it. Like this is really the limiting MMSE of this problem. Like it's really the MMSE has a combinatorial interpretation. If you do not care about the specific notations and L2 error, etc., is really 1 minus how many edges, what's the fraction of edges I can possibly recover from G. Okay, so this is the perspective. So in particular, like if P is 1, you expect this thing to be 1. Right, so this is the maximum value because you cannot recover anything. And if P is 0, you expect this thing to be equal to 0 because you can recover everything. Right, so you understand the scale of things. So the MMSE in this way, it's in between 0, 1. 1 is trivial, 0 is everything. Okay, hopefully that makes sense.
Sorry, what do you mean by recovered?
Recovered. So it means exactly what I'm saying, I guess. So it means that I can identify them from G. Say these are the edges of PC.
That are for sure from the planted clique.
Like right. Perhaps it's good to keep this in your mind. The proper, this is intuition, right? So the proper thing is this. Like we'd say, corresponds to guarantees like with high probability, these are the edges of the planted clique. But I'm skipping this and I'm just telling you the intuition. That's how you should understand this. But yeah, if your formal thing is with high probability recovering the edges of the class.
I see. Thanks.
Okay, so that being said, and keep this in your mind, the answer to this we know. So the answer to this we know. In fact, we know like it's a very step behavior, like revealed into this object. So what's happening is that like you have here the planted clique, and oops, I skipped colors. So let me do this differently. So if this is the planted clique, and you have like let's say all these outside edges, then basically what happens is the following. Not only the MMSE is 1, like trivial, like you cannot recover any fraction of edges if P is 1. This happens all the way if P is bigger than half. Okay, so if P is bigger than half, this is trivial. And if P is less than half, there's a subphase transition that it goes to basically another form of trivial. You can recover everything basically. Like you can recover the best trivially bad, right? So this is trivially bad, and this is trivially good. You can recover nothing if you want if p is bigger than half, and you can recover everything if p is less than half. Like you can recover like almost all the clique if p is less than half, and if the noise is small, less than half, and above half, suddenly you can recover like not a non-trivial fraction of edges. And you may be thinking, what's the magic thing that happens at half? Where the outside part is a GNP, right? So it turns out that this is exactly the value of p that GNP stops creating a k-clique by itself. Like this is the value of p where the randomness, the noise will create a k-clique by itself. So if p is bigger than half, there is many such cliques if you want, and the problem is hard, like to distinguish. It's impossible to distinguish between planted clique and the k-clique. But if p is less than half, there is basically no such k-clique, and one could think intuitively that you can find the planted clique.
Are you assuming that p is fixed, or if it's scaled with n?
Right. So this problem here is specifically, I'm assuming that p is fixed for this statement, but in fact it holds, for any p bigger than half that has like, let's say, some constant gap, let's say here. You can push the constant to 1 over log n if you want. Yeah.
Yeah, got it.
So this intuition, by the way, like to make this a proof is not that easy. Like, but this is the intuition why at half is the critical thing. But it's also not that hard. So in fact, it's a fun exercise for a class if you want to work around the posterior and calculate with Bayes rule and do your favorite first and second moment methods. It's a nice exercise if you're teaching a graduate class in high-dimensional statistics, like to make this to understand this phase transition. And let me also say the interpretation again. If p is less than half, then almost all the clique is recoverable. If p is bigger than half, then none of it is recoverable. And this, in fact, has a name. It has a name in the literature. We call it the all or nothing phenomenon. It has an interesting line of work on this. This subphase transition from 0 to 1, we first saw it in sublinear sparse Gaussian regression. And it was interestingly not predicted by statistical physics methods exactly because of this sublinearity. And if you're thinking where sublinearity is here, this is an extremely small clique. Right? So perhaps the natural guess, if you see this and you have the perspective of trying to find the MMSE for various models, you could be thinking, okay, maybe all sublinear sparse, like where your hidden signal is very small compared to the universe, is exhibiting this jump, this 0-1 jump. And that's perhaps a natural question out of this analysis, but it's easy to refute it. So if you go to the next perhaps canonical thing you can do, which is okay, if you know what happens if you plant 1 clique, how about if you plant 2 cliques? So if you plant 2 cliques, what do I mean by this is the same story, but you're planting not only like 1 clique, you're planting another smaller, let's say, and everything else is with probability half. With probability p. So if that happens, right, you're trying to recover now the disjoint union of 2 cliques. And okay, just to put perspective, let's say one is logarithmic, the other is twice logarithmic like before. And you can ask again the MMSE. Again, this is the same perspective. 1 minus expected value, the best fraction of edges. Now of H, right? H is like this disjoint union of the 2 cliques that can be recovered from G. Okay, so like what's the ratio of the fraction of edges you can recover? And it turns out this exhibiting a 2-step behavior. So the perspective is that is as follows. You plant these 2 structures, and you are asking, okay, where can I recover? And it turns out, of course, like before, if p is 1, this is trivial, but turns out all the way to be bigger than half, this is trivial. You can basically recover nothing in this regime, like an asymptotically 0 fraction of the edges of the structure. And if p is less than a quarter, it turns out that you can recover basically everything. So like both asymptotic, the asymptotic fraction goes to 1 of the edges you can recover. But something interesting happens in between. In between, there is a phase where basically you can recover something if you want. Like you can get like some non-trivial fraction, not 0 or 1. You can call, in fact, the 4/5 of fraction is what you can recover. And you may be thinking, what is the 4/5? How does this appear? Is because in this regime, actually, you can recover the biggest clique. Like that's what happens. Like in this regime, you can recover the strongest component of the signal. The noise is low enough that you can recover like the biggest clique, but small enough that you cannot recover the smaller clique. And if that makes sense, it's not as a fun exercise for a class, even with this example. Oh, please.
Sorry.
Yes, okay.
Yeah, I just like, so you mean like you could still recover a tiny bit from the small clique because it's like 4/5, right?
4/5 is exactly, no. So 4/5 is, I'm referring to the edges, and that's very important, not the vertices. So these are the vertices, and the ratio of the edges is 4/5 exactly, if that makes sense.
Oh, I see. So, you're right. So it's basically could only recover the big clique and nothing you could tell for the small clique.
Yeah, nothing from the small. Yeah.
Got it. Thanks.
Yeah. And that's an interesting phenomenon. It already shows that this planted subgraph is having like these trade-offs in terms of recoverability. Even with 2 clicks, there's some interesting story here. And what I want to say is that not as a fun exercise. If you're teaching a class, you can do this. You can do this with direct posterior analysis. You can analyze what's the posterior. You can take the mean, but it's really like a couple of tens of pages to get to this, and maybe it's not a good exercise for a class. And really but it highlights the question of like if we get confused already to this. Like, is there some general theory underlying this of general rule of what's happening here in this model of recovering planted structures in noise, and specifically for subgraphs? And this is the question that motivated this work. And again, the sublinear nature of this problem doesn't make it amenable in principle, and combinatorial kind of nature doesn't make it in principle amenable to the statistical physics method. So you have to think differently. And it's time to introduce the planted subgraph model. So the planted subgraph model is defined as follows, perhaps what you're expecting. So there exists this arbitrary subgraph now. Now you choose your favorite subgraph, right? It could be you really like the clique, so that's your favorite subgraph. You may like the disjoint union of 2 cliques. You may like a matching. You may like a half a matching, a spanning tree, a bi-clique, whatever. So you fix it, and this is the graph you care about. And then what happens is you embed it somewhere uniformly at random on n vertices. So you embed it somewhere here. Okay, so a copy of H. And then you throw every other edge with probability P independently. So you take the union with the G and P. So like you take the union with the G and P. And you notice that in the embedding here, you might have an edge inside that you're adding, etc., etc. Because H doesn't need to be a fully connected subgraph. So then the question remains, right? Can you find H from G? Now it's an arbitrary, complicated combinatorial object. So again, though, the perspective is the same. This is 1 minus the best fraction of edges of H that one can recover from G. Okay? And you want to understand this as P, grows. And okay, so this generalizes model generalizes many models studied in the literature for various reasons. I mentioned the planted clique and planted bi-clique. These are community detection motivated models. There is, of course, the planted matching. This initiated by some desire to understand the toy model for recovering a video from slices of it. Planted trees have been studied, and really everything. You can planted Hamiltonian cycle, like all these things have been studied. So really, this unifies everything, like in that realm. And one bad thing about this generality is that now you cannot really talk about limits of this object. And it's a very technical reason, but you're constraining nothing here. You don't constrain H to behave nice in any way. So it could be this weird thing that like for even n, you're choosing 1 clique, and for odd n, you're choosing like the disjoint union of 2 cliques. So if you're doing this, then the curve will oscillate between like going to the planted clique MMSE and the planted 2 cliques MMSE. So of course it will not converge. So it doesn't make sense to talk about limits. So the more natural perspective is to talk about the MMSE for large but finite n. So this is the perspective we should have. Like we should think about large n but finite. In the general, if we want to build a general theory. And if you're thinking, how does this function even look like? I mean, if you just because of the product distribution, the Erdős range distribution in the noise, really, I mean, if you expand everything, this is a polynomial in P. So, it's just a polynomial in P, but the degree is very high. So in principle, it can, converge to arbitrary complicated functions. And of course, it increases with the noise, right? Like the more noise you have, the error gets larger. Okay, so with that in line, let me tell you our result. The result I want to describe from this work is basically a complete characterization under one mild assumption on H. So we prove basically for any planted subgraph that is weakly dense. So we only assume a mild density assumption. So what is a density assumption? Usually when you say a subgraph is dense, you say that the edges, by the way, the cardinality of H for me is always the number of edges. I think of it as an edge structure. The number of edges, when it's quadratic in the number of vertices, usually you say that's a dense subgraph. If it's linear in the number of vertices, you'd say it's a sparse graph. It's a sparse subgraph. A weakly dense means it's a little bit more than linear. So you have an extra logarithm here. So as long as it's weakly dense, basically we characterize this MMSE curve. And how do we do this? How do we get around all these possible combinatorial ways H could be?
Ilias,
yes.
I have a quick question. So you're saying that if the number of edges is linear on the number of nodes?
Yes.
Or this is a bit more than linear, like it's n times log n at least? That's what you're saying?
So first of all, I'm referring to the vertices of H, not n, of the full graph, right?
Oh, yeah.
Yeah, and yes, I'm saying I call it weakly dense if it's V log V. If it's like, it has an extra, it's grows a little bit faster than like linear.
Okay.
Makes sense?
Nice. Yeah, thanks.
Right. So what the result is that the MMSE curve for large n is basically always approximately a piecewise constant function. So this thing behavior we saw is actually not an artifact of this specific example. It's always a piecewise constant function where we characterize the discontinuities, and the discontinuities up to a very small error, like 1 plus L1 error. And interestingly, and perhaps somebody can argue the most interesting thing about this result, or one of the most interesting things, these discontinuities are given by a very fundamental quantity in probabilistic combinatorics, which is called the subgraph Kahn and Kalai threshold of H. So I will explain what this is. You don't need to know, of course. But it actually gives a new meaning, which is statistical, to a very well-known quantity in probabilistic combinatorics that doesn't have any principal reason to relate with statistics. And we actually characterize even more. We can understand in every noise regime which exactly subgraph of H is recoverable, like we did for k-cliques, where we understood is the big clique that is recoverable. We can do this for any H and tell you which subgraph is recoverable given the noise. And we do this by essentially defining a certain peeling process that we call the onion decomposition. And if you are thinking how complicated these objects are, they are functions of H. I mean, you just need to know H to calculate those objects. And they're in fact polynomial time computable objects. So, they are, the complexity at least are not that high to characterize these things. And, they can get a bunch of corollaries, for example, from this result. For example, you can say, okay, when do I see the 0-1 behavior? That like, I can recover everything and then I can recover nothing. Well, that happens if and only if the hidden subgraph is so-called balanced. So that's a standard graph theory notion from the 70s in graph theory, and it completely characterizes when you see the 0-1 law. In fact, it was the main result in a previous paper I had on this line of work that you get as a corollary of this generic principle. And I will not talk about proofs. That's already a complicated setting. But just if you're interested, the proof follows by upper and lower bounding the MMSE in two ways, and by this this piecewise constant function. The upper bound follows by some minimax duality over discrete spaces that goes beyond these classic convex concave minimax dualities. It's because over discrete spaces you might find interesting. And the lower bound follows by some sort of Bayesian perspective on another Kahn-Kalai thing called Kahn-Kalai conjecture in probabilistic combinatorics we recently had. Okay. So now we'll try to get through this. Of course, time is I will try my best for the time, but I will try to give you a more concrete thing, at least of the first point here. Okay, so this is what I'm going to talk about. Great. Let me make this precise, especially because these things are probably completely unknown words. Okay, so to describe these words, I need to give you a little bit of background on basically random graph theory. A very related question, but also very fundamental in random graph theory and very classical is the following. Erdős and Rényi themselves asked the following question about the so-called for any h to find the critical threshold for h. Okay, so here to understand this, fix any h that, your favorite subgraph again, it could be an h that doesn't depend on n. It could be like a triangle. Or it could be an h that depends on n, like a log and clique or a matching. And you can ask the question, for which values of p do I expect to see a copy of h in an instance of G and P? Okay, so when do I expect to see this pattern in the noise, as I call it, but in the Erdős-Rényi instance? And of course, if p is 0, there is no hope, right? There's nothing there. And if p is 1, then of course you can see everything. So really it's a threshold question. Like, how does p need to scale with n? Okay, it's a very canonical thing to do. And if you come to think about it for a second, the question mathematically is this. There exists a copy of h in G, where G is a random variable, right? G and P. So of course, how can you handle this? Well, the trivial thing is to do a union bound, right? So it's you just do a union bound here, like over all the copies of h, and it's an easy thing to get some upper bound. For example, that's also called the first moment method, I guess. And if you do this, then if you send this to 0, like if you manage to choose a p, so that for some p this goes to 0, of course this thing is going to 0, right? So therefore, with high probability, there is no copy of h for this p. So if you optimize this whole procedure, you get what's called the first moment threshold of h, which is basically the optimal union bound threshold, which basically, like if p is less than this, there is no copy of h. And in particular, the so-called critical threshold, where this becomes possible from impossible, is above this, right? Because for this value, there is no h. And okay, and if you just do the math with what this thing really is, I mean, there's no reason to explain this in detail. It just turns out to be asymptotically like n to the minus vertices over edges of h. That's the value of this. And of course, you can think, okay, is this union bound always tight? In some cases it is, but it's not. And the key idea though from the 70s is that basically this is almost tight. And it's almost tight for the following very nice reasoning, that what you can do is to make this trivial observation that if there is a copy of h in G, then there is a copy of S in G, where S is any subgraph of H. Right, it's very easy. So what I'm saying is that like for any S in H, the probability there exists a copy of H in G is at most the probability there exists a copy of S in G. And then you can do the union bound for S. Therefore, what this means is that if I make this go to 0 now for some p, then I make this goes to 0 and this go to 0. So in particular, I can take the union bound threshold, the first moment threshold, and that's already a lower bound for the critical threshold of H. But for the union bound threshold of S, if that makes sense, is another lower bound on PC of H. So what does this mean? Is you can take the maximum, right? And that's potentially a better threshold, a better bound, sorry, on PC of H. And that has a name that's called the subgraph Kahn and Kalai threshold. And of course, if you do the math with this formula, you get like this. That the Kahn and Kalai threshold is basically n to the minus the minimum overall S of vertex to edge ratio. And okay, Please, any question?
So if I set h equal to k-clique with k equals 2 log n, then the bound is very loose. It's going to be like 1 over n compared to 1/2 that you had earlier.
No, the bound is tight, actually. The bound is tight. It turns out that if you do the math correctly, this is tight. It's exactly 1 over 2 log 1 over log n to make this half, basically.
I see.
Yeah.
Okay.
Yeah.
Okay, thanks.
In fact, on this is actually Bolobas proved in the 80s that this is always tight for any constant subgraph. So not what you're asking, but like if H is like a triangle of like a rectangle, you know, this is always tight. And in fact, and then from this point on, people have written like millions of papers on like special cases. So like, for example, log and clique is one of them. This is an easy thing, actually. I mean, sort of. I mean, to conclude by a second moment method that you can do this, but there's papers on perfect matching, etc., that it's like kind of almost tight. And in fact, that led to a conjecture by Kahn and Kalai in 2004 that this is always tight up to a logarithmic factor for all H. And very interestingly, over the last 6 years now, people have actually proven variants of this conjecture. So yeah, the story goes a little bit more. Like Talleyrand gave a version of this conjecture, and basically over the last 5 or 6 years, we saw by 2 papers proofs of variants basically of these conjectures, which are like known as the Kahn-Kalai conjecture and the fractional Kahn-Kalai conjecture, or whatever is one. And so this is really a good logic. You know, it turns out to be correct after many years of work and big breakthroughs. And in fact, also some relevant thing to this work is that we figured out also a way to do it using Bayesian statistics. Like we offered another proof in 2022 of this result. And that's actually relates with this work, how it ended up being possible. And let me also say that, by the way, that being said, this conjecture, that this is tight, is in fact actually a variant which is still open. So there is like a work on this that people try to make this work, but it's still open. Okay, now that you have this Kahn-Kalai perspective, I can tell you actually the main result. So, okay, so what does this have to do with, hopefully intuitively you get there is something there, some relation, but let's make this precise. So how do you connect this? So then you're asking, the right thing to do is to think the MMSE as a threshold question. So how do you do this? Well, you fix a Q, and you're asking, when is the MMSE crossing the value 1 minus Q? In other words, by the interpretation I told you, what is the value of P that one can recover a Q fraction of H? Right, I care about Q 2/3. When can I recover a 2/3 of the edges of H? Of course, again, right, if P is 0, this is always happening, right? Because there is nothing that I can recover the full thing. So of course I can recover a Q fraction. But if P is 1, then I cannot recover anything. So of course I don't recover a 2/3 fraction. So it's really a criticality question again, right? You know, what is this? Oops. What is this critical thing here? And okay, so we have to make a guess of when is this happening? When can we recover a Q fraction? And here is a somewhat bold idea, a bold conjecture of when this is happening. So what could be a problem, right? So what could be a problem in finding this hidden H? So here is one way that seems problematic. If to recover a Q fraction, this is what the perspective is, to recover a Q fraction, the perspective is if there exists some S, which is small here, small I mean smaller than Q times H, like it contains less than a Q fraction of H, that the noise is actually creating an H minus S, so that the full thing with S looks like an S. If that happens, basically, it seems natural to guess that the recoverability, the statistician, let's say, would be confused. Like, is this the real H or this the real H? And the best guess would be to output any of them, but then it will output something with less than a Q fraction, correct? So from this point of view, which doesn't seem clear that this would be actually, you know, the tight thing, the tight criterion, one idea would be to find, okay, when is there such a distractor, if you want, such an S that can create that problems? So with the noise. So basically you can say, okay, here is one criterion of where you can recover a Q fraction. Whenever there is no S that is small, smaller than Q times H, that H minus S as a graph appears in G and P, in the noise, right? This will be perhaps a criterion of when we can actually recover a Q fraction. If that makes sense. And okay, this somewhat wild guess, admittedly, gives rise basically to this formula, though, because now it's all about G and P, right? You have removed the signal. It's all about the behavior of the noise. And if you do this, then the quantity is this, right? It's the minimum over all S, which is smaller than QH, of the critical threshold for H minus S to appear. Okay, so that's a guess. Now, the bad thing is that this guess is not easy to work with, because I told you that these objects are very hard to calculate, right? I mean, like we have conjectures about them, recently proven, they're complicated formulas. So how are you going to go around this if you also want the minimum over S? So one guess is like to trust that the subgraph Kahn and Kalai conjecture is true. And say, okay, so let's trust that this Kahn and Kalai conjecture is true. And then replace this by the Kahn and Kalai variant, which is actually an easier thing to compute. In fact, if you just, it was like, n to the minus vertex over edges, and, it's just a maximum overall subgraph of H minus S. So you end up with this, okay, it's not great, but it is something, like a guess. It's like this min-max formula of what it is, the threshold. Okay? Turns out that even if we don't prove the subgraph Kahn and Kalai conjecture, this is a correct thing. Like this thing is correct. Like this is governing the Q recoverability of H. So let's give a name to this. I will call this phi of Q. And let me just do this here. Just is the same object. For any Q, let phi of Q, basically the expected minimum P, or the conjectured minimum P, so that like H minus S appears in the noise, and S is small. Okay, these are conjectured thresholds. And let's make some sense at least of this object. So if Q is 0, right, you're minimizing over nothing. So so if we minimize over nothing, then phi of 0 is basically just like there's the empty H minus the empty set. So there's the Kahn and Kalai threshold of H. So we cover this fundamental object from probabilistic combinatorics. And if phi1 is 0, if Q is 1, then you are allowed to choose S equal H. So this becomes the empty set. So of course, like, the minimum such P is 0. Like, of course, you always will see the empty set. And of course, another thing is, phi Q decreases, because as you increase Q, this is expanding. Like this region is expanding. Okay, so here is the main theorem. The main theorem says the following thing. Basically, for any weakly dense H, there exists a series of M numbers where this M depends only on H. Okay, not on N, but on H. So M numbers, Q0 is 0, it starts from 0, and then it's less than Q1, and then Qm, which is 1. Perhaps, okay, M plus 1 numbers, to be correct. So that the following thing happens. So instead of reading you the theorem, I will draw a picture. So the following thing happens. So I will draw it here, and then I have a better one in the next slide. Okay, but let me do it first here, or attempt to do it here. Okay, so this is P, and this is the MMSE. Okay, so MMSE again is really 1 minus the best fraction that you can recover. So what happens is that, okay, so this is 0, 1, right? So both of P takes values 0, 1, and the MMSE takes values from 0, 1. So, okay, if P is 1, then as we said, there is no hope, right? There is nothing you can do to recover anything. So it starts from here. Like it's the best fraction you can recover is 0. And then basically this continues in a flat line all the way to some P, right? It's impossible at all to recover anything all the way to some P, which basically we completely characterize what's the first P you see at jump. This is basically phi Q of 0, which is just phi of 0. It's given by this threshold at Q equals 0, or at Q0 if you want. And then you see a jump. Okay, you see a jump. And this jump moves you down to 1 minus Q1 for this Q1. Okay, so you can recover suddenly Q1 fraction of the edges. And then this continues in a flat way until it jumps again And these jumps now, it's happening at phi of Q1. Why? This is exactly where recovering a Q1 fraction becomes possible from impossible. At least this was what we expected when we defined this threshold, and indeed that's the case. And then it jumps to 1 minus Q2. And this continues until it reaches 0, basically, at some point. So this is basically what this theorem is telling us. And these thresholds are correct up to very small error, like 1 plus little low of 1 error. And all these objects are computable given H. Okay, I expect this might be difficult to pass, so let me actually give you a better picture here. So this is exactly the same picture, but better and making more light. So here is one H that has like 4 jumps. So this is basically impossible, like all the way to phi Q0, which is phi of 0. And then it jumps, it goes to 1 minus Q1, and interestingly, this exactly remains impossible up to phi Q1. Then there's another jump, it goes to Q2, another jump, and another jump. Okay, hopefully that makes some sense. Now, what I want to say is to focus on this object for a second. So this object here is the first jump. The first time the MMSE becomes non-trivial, that you can recover something. Well, come to think what this object is, as I said before, this is phi of 0, which is the Kahn-Kalai threshold of H. So basically, one outcome of our result is that the first time you can recover something happens at P, which is exactly up to 1 plus little of 1 error, the Kahn-Kalai threshold of H. So this is what I want to say here is basically that the first discontinuity of MMSE is given by this. And in fact, I want to say that in statistics, this thing has a name. This is called the weak recovery threshold of the parameter. And because it's the first time you get some weak recovery. So the weak recovery threshold is basically given by the Kahn-Kalai threshold in combinatorics, which is a fundamental thing for many decades in probabilistic combinatorics. So what I have this here, I have this written down. For all H, the subgraph Kahn-Kalai threshold is the weak recovery threshold. So this connects to communities, if you want. And also, if you're familiar with statistical physics, this has a name. The weak recovery threshold is usually denoted by when the system condenses. And it's called the condensation threshold. So, the condensation threshold is the subgraph Kahn-Kalai threshold, exactly. And, this gives a meaning to something that's only conjectured to have a meaning in probabilistic combinatorics, not yet has a meaning. But it's actually very, very clearly have a meaning, even not up to a logarithm here, like exactly has this meaning.
Sorry, is Q0 exactly 0?
Yes.
I see.
Yeah. Yeah, okay, so here is perhaps setting a little bit more light into this. So there is a way to get more light of what was just said by this peeling process I hinted before, which is called the onion decomposition of H. So let's do a process together to understand this. So if this is H, let's do the following iterative algorithm on H, a copy of H, whatever H it is. So, okay, start with S0, the empty set. And then, in the first step, choose the so-called densest subgraph of H. Okay, so choose the subgraph that has the maximum edge to vertex ratio. Okay, that's called the densest subgraph of H in this sense. This will be our S1. So the densest subgraph, that's the more strongly connected, subset or community inside H. Then choose the densest subgraph that contains strictly the densest subgraph S1. Oops. This will be S2. And continue doing this, right, until you completely exhaust H. So it turns out that this peeling process we call the onion decomposition of decomposing H has a lot to do with recovering H in noise. Why? Because it turns out that actually this is the subgraphs you recover in the different regimes. one can recover optimally statistically in the different regimes. And here is the actual theorem, in fact. For the onion decomposition, the QIs are just given as functions of SIs, basically as the fraction of edges the SI has compared to H. And there are some simple formulas also for the SIs. And perhaps the easiest way to put it is by this diagram here to see the actual theorem. So the actual theorem that makes more sense, I think, than what I told you before, is if this is an H, and that's the onion decomposition, so QI here is just the fraction of the edges of SI over the edges of H. So this is like, this is the densest subgraph. How many edges does it has? It has a Q1 fraction. The densest subgraph that contains the densest subgraph has Q2 fraction, and it continues, right? So it turns out that like this is governing the MMSE curve. So let me explain. If P is 1, then as I said, you can recover a zero fraction, right? This is 1 minus 0. And indeed, in this whole regime, what you can recover, the best thing you can recover is really the empty set, right? I mean, you cannot recover anything better than this. But what happens in the first jump is that you can able to recover something which is a Q1 fraction, and this exactly because you can recover exactly the densest subgraph. As the noise gets smaller, the first thing that gets revealed is the densest component of H. And then you continue, and the second thing that gets revealed is the densest, like suddenly gets revealed, the next thing that gets revealed as the noise decreases is the densest subgraph that contains the densest subgraph. And basically like this continues all the way to the end. So that's the actual theorem. And these PQIs are exactly interpretable as the noise levels where SI is appearing in GNP, subject to the Subgraphs and Kalai conjecture. So this is exactly when this pattern emerges in the noise. So this is kind of what this explains this picture more. I hope that is making some sense. Right. So let me tell you that this is a very applicable perspective, in fact. So for example, you can apply it in the problems I said before. So for example, plant and click, right? So plant and click, here is your H, right? It's just a fully connected thing. And I told you it has a zero and low. Can we see it by the onion decomposition? We can. Why? Because the densest subgraph of H is H, like it's a click. So the densest component is H. So the onion decomposition has only one step. And of course, the one step means one transition, like from top to bottom, because it needs to go to bottom. And of course, the location of the threshold, so Q1 is 1, and the location of the threshold is easy to compute. The Kahn and Kalai threshold is half in this case. So really, directly, no posterior analysis whatsoever. The MMSE jumps from 1 to 0 at half. So this proves this result in one line. What about two clicks? Well, if you have a smaller click and a larger click, what's the onion decomposition? Well, the densest subgraph is exactly this, like the largest click. So S1 is the largest click. So let's say larger and smaller. And what's the densest subgraph that contains the densest subgraph? Well, the whole thing. So two steps, so therefore two discontinuities. So you get exactly like this picture here. That's what I'm saying here. And of course, you can compute these thresholds very easily by the formulas we have. So you get exactly like you can recover the densest click and then etc. So that's what I want to say. Let me just conclude perhaps with some questions in some skipping material. So we in fact can get rid of the weakly dense assumption, but it's somewhat a weaker theory. So we can then, if you have a completely generic H, and in fact we can deal with completely general monotone properties if you want the more jargon in this field. If you plant arbitrary monotone properties in random noise, then the thresholds are again there. They're given by something more complicated called the fractional Kahn and Kalai thresholds in probabilistic combinatorics. And what's the weakness? The weakness is we cannot get the constants right. So this is correct only up to constants. So not 1 plus log of 1, like we just had before, the accuracy of the discontinuities. And that being said, let me just tell you quickly some problems. So One very canonical model is the so-called perfect matching problem, where you plan the perfect matching, and that's not a weakly dense graph. And in fact, figuring out the constants there is actually a topic of many recent papers. So yeah, I mean, this is, for example, a very interesting sparse thing we're missing right now, which is it has a big impact in the literature if it's solved. At a more higher level, I think, planet subgraph is interesting, but of course, the toy model, like the interesting thing I think we learn from this is this hierarchical learning perspective, that if you try to learn a very difficult concept, you do this in a staircase manner. You first learn, the most obvious thing, and then you sort of continue and build through it. And that's a phenomenon that people have seen over the recent years in learning of neural networks as well, and how stochastic gradient descent in learning them by first learning the biggest component, et cetera, et cetera. And I think this builds something that will be probably some very unified theory about MMSE, or or the mean square error of natural algorithms, about having these staircase features. And finally, if you like probabilistic combinatorics, I mean, we did all this work, but none of this is actually directly implying the subgraph and Kalai conjecture. So it's still open. People are working on it. So it's a nice problem if you like these things. And yeah, last but not least, let me tell you that, like in the random graph theory, where people were working case by case for years, and then Kahn and Kalai suggested a unification of understanding these structures. I think it's a sort of, similar perhaps thing that, like, sometimes if you think in generality, you can come up with these rules that you cannot see if you study, a paper for any different age. Kind of, and you have this perspective on, like, the onion decomposition, for example, just by arguing in generality. And yeah, thank you very much. Yeah.
Thank you, Ilias.
Pleasure. Yeah.
So we have a few questions in between, but there's time for another question if anyone has one.
Yeah, thanks a lot, Ilias, for the great talk. I had a question. Are there phenomena that we can know MMSE, but we cannot recover the corresponding subgraph? Because then, I mean, I understand here you can recover the actual subgraph as well.
Recover? You mean we know which subgraph is recovered? Or something
Yeah, for
else?
example, I mean, I know the MMSE, but I cannot find the planted clique itself.
So I'm a little bit confused with finding the planting. So so if the MMSE is small, it means you can recover a subset of H, right? That's kind of equivalent with it.
All right.
Now
But if it's not small,
sorry, what?
but if the MMSE is not small,
Mm-hmm.
then it's not clear. I mean, I
No,
see.
it's a one-to-one mapping. If the MMSE is small, there is a subset that you can recover. Perhaps the contribution of this is that we characterize which is the subset. So it's the densest component. It's not that there exists a subset. A subset exists, but makes sense.
Right. Yeah.
We characterize which is the subset. Yeah.
Mm-hmm. Got it. Thanks.
Any other questions? Okay, I actually had one. Something that I'm not too familiar with this area, but I noticed when you're planting the graph, you're also adding edges inside the planted graph. So is that really critical, or maybe just simplifying?
Yeah, it's a big. So there is a literature also on people who keep this graph and induce subgraph, so they don't touch the inside. It depends on the perspective. It does make life much simpler.
Mm-hmm.
In terms of it's because the noise is just additive there, right?
Yeah.
You just add it, but the noise. I believe most of these phenomena will appear also in the induced subgraph, but yeah, I don't see a reason why the other is more canonical, so we didn't pursue this. But yeah, it is a good point though.
Mm-hmm.
There are some applications in cryptography where it makes more sense to do induced subgraph, but yeah, I guess it gets a little bit more niche. Yeah.
Mm-hmm. Thanks.
Thanks so much. I don't have any question. I'm just I think it's a great work. It's connected everything, and this onion decomposition, the step functions, is like it's incredible. I like it very much. Thank you so much.
Thank you, Sophie. Good to see you. Yeah.
Yeah, great talk, Ilias. Thank you.
Thank you guys. Yeah, good to see you.